Hello students, today we will discuss regarding the energy stored in a capacitor, the various expressions which a capacitor stores in the space between its plates in the form of energy, and also we are going to discuss the expression for the energy density of a parallel plate capacitor, right? So let's start with the topic. We are going to deal with this energy stored in a capacitor. So as you are aware, this is the symbol for a capacitor. Suppose its capacitance is C. Area of each plate be A and say let B be the small separation between the two plates under consideration, right? Let us consider the two plates of the capacitor be connected to a source. This is the source, which will maintain a constant potential difference across the plates of the capacitor. Now, in order to charge the capacitor, this source has to do some work. That amount of work or energy spent by the source is stored in the capacitor between its plates in the form of its energy. So we need to find out the expression for the energy. So what I have stated is, the energy is stored in the space between the plates of the capacitor at the expense of the energy spent by the source, right? When the charge is sent by the source, its potential gets raised. Suppose dq is the charge sent by the source at constant potential V. Then, small amount of work done by this source in sending charge dq is given by dw is equal to V dq. Now, where has this come from? It is as per the definition of potential difference. Potential difference across the plates is V. Now, as per definition, potential difference is work done per unit charge in moving this charge from one point to another point, isn't it? So, from here, dV is equal to V dq. Again, I am repeating. Whatever energy is spent by the source in charging the capacitor, the same energy gets stored in the capacitor, right, in the form of its energy, whose expression is to be determined. So here we have considered dq with the charge sent by the source to the capacitor at constant potential V. So the small amount of work done by the source in sending charge dq to the capacitor at constant potential V would be given by dw equals to V dq, right? As q equals to CV, C is considered the capacitance of this capacitor. So V can be written as Q by C. Therefore, dW it is equal to Q by C dQ. Now, in order to find out the total amount of work done, we need to integrate it. So, therefore, total work done it would be given by Q dQ. Right? C is the capacitance, which for a given conductor or a capacitor is constant. As we are aware, it simply depends upon the dimensions of the conductor as well as the medium in which the conductor is placed, right? In this case, the nature of the medium between the two plates. Integration of Q, that would give us Q square by 2. So what you get is, so therefore, work done by the source in charging the capacitor is given by Q square divided by twice C. And as I have stated as per the work energy theorem, this work done by the source in charging the capacitor gets stored in the capacitor between its plates in the form of its energy. So, this is the expression for the energy, half Q square by C. Put this as equation A. This is the expression for energy stored in the capacitor in terms of charge and the capacitance. Now, using this expression, we can also find out various other formulas for the energy of a capacitor. Like, we know that Q equals to CV. Therefore, energy can also be written as, in place of Q, you can write CV. So, Q square becomes C square V square. So, we will be left with half C square V square by C. That is, energy is equal to half CV square. This is another very important expression. This is B. There is still a third expression for the energy, right? So what to do is, again, we'll make use of this. Now we'll eliminate C. So energy, it can become Q square by twice. In place of C, we can write Q by V. QV. So what you get is, energy is also half QV. So these are the various expressions for the energy stored in a capacitor, right? Half CV square or Q square by twice C or half QV. These are the three expressions for the energy stored in a capacitor. Now, which formula is to be used, right, at appropriate situation? What I mean to say is that C is constant, as you are aware. Capacitance of a given capacitor is constant. Now, in the series grouping of capacitors, the charge across the plates of each of the capacitor remains constant. So, in the series grouping, Q being constant, it is preferable to make use of this particular expression, right? Half Q square by C. So, for series grouping, since Q is constant, so this is the expression to be used. It is the preferred one. While in the parallel combination, where V is constant, make use of this particular expression. In such a scenario, energy stored would be directly proportional to capacitance. So these two do not different or do not contradict each other. One might say, over here energy is inversely proportional to capacitance, while in this case energy is directly proportional to capacitance. But they are not contradicting each other. Energy is inversely proportional to capacitance only when charge is constant. While on the other hand, energy is directly proportional to capacitance only when the potential difference is constant. So there is no contradiction in these two expressions. So students, please remember this particular point, right? In the series grouping where charge is constant, make use of this particular formula, right? It is the preferable one. And in the parallel grouping where V is given to be constant, make use of this particular expression. So energy is inversely proportional to capacitance only when Q is constant. Energy is directly proportional to capacitance only when V is constant. So both represent the same thing, they are not contradicting each other. So these are the various expressions for the energy stored in a capacitor, right? Now what to do is, we will discuss the energy density. Now energy density is the energy stored in a capacitor per unit its volume. That is known as energy density. Density per unit volume, right? So let's find the expression for the energy density of a parallel plate capacitor. So as I have stated, energy density may be defined as the energy stored in a capacitor per unit its volume. So let's find out the expression for energy density, right? So of a parallel plate capacitor, these are the two parallel plates under consideration. Both the plates are identical. Suppose each of area A, and let us consider the separation between them is small d, right? And if it is given positive charge, you are aware, negative charge will be developed on the inner face of the second uncharged conductor, and if it is earthed, then the positive charge developed on the farther face will get neutralized, right? So this is a parallel plate capacitor. Now look, it can be joined like this. It will occupy some volume. So what will be the volume of the capacitor? Volume of parallel plate capacitor would be cross-section area multiplied by the distance between the plates. This will be the volume of the capacitor. And energy density, as I have stated, energy density is defined as the energy possessed by the parallel plate capacitor per unit its volume. That is energy divided by volume. So what will be the SI unit of energy density? Energy per unit volume. So energy is joule and volume is meter cube. So its SI unit would be joule joule per meter cube. This is the SI unit of energy density, right? Let's substitute the value. Just now we have discussed the expression for the energy, right? It's half CV square or Q square by twice C or half QV. So one of the expression for the energy is half CV square. Volume, it's cross-section area of each of the plate multiplied by the distance between the plates. So this is energy density. Also, we are considering the case of parallel plate capacitor. We have derived that the capacitance of a parallel plate capacitor is epsilon A by D, provided the space between the plates is air or vacuum. In case of any medium, it would become K epsilon A by D, right? Here in the present scenario, we are considering air or vacuum to be the case. So, also, let's write potential difference in terms of the electric field. Now look, electric field is along this direction from positive plate to the negative plate, along the direction of fall of potential. And V is the potential difference. So what's the relationship in potential difference, electric field and this separation? We are aware that V is equal to E into D. This is the expression for the potential difference. Electric field in magnitude is given by the potential gradient, right? So from there, you can easily get V equals to ED. The potential difference across the plates is given by the strength of the electric field multiplied by the distance between the two plates. This is valid only when electric field is considered to be uniform. Substituting these two values over here, what we get is energy density. It would be equal to half C, which is epsilon A by D, capacitance of a parallel plate capacitor. V square, it would be E square D square divided by volume, which is A into D. So we are left with half D square get cancelled, A get cancelled. We are left with half epsilon E square. So this is the expression for the energy density of a capacitor. So again, I must repeat, energy density is basically the total energy stored in the capacitor per unit its volume. Here I found the expression for the energy density of a parallel plate capacitor. So student, this is the result. Now what we can do is, we can find out the expression for the total energy of the system when the capacitors are connected in series, and in the next case when they are connected in parallel. So let's find out the expression for the total energy of a system where the capacitors are connected in A part series and B parallel, right? So let's proceed further. So energy of a system consisting of many capacitors or group of capacitors connected in series or parallel. Let's discuss the first case, that is series grouping. Okay, these are the capacitors which are connected in series, suppose. Let's consider the case of 3 capacitors. You can generalize to n capacitors as well, right? So suppose this is of capacitance C1, C2, C3. In series, charge would be constant, right? And let the potential difference be V1, V2 and V3 respectively across these 3 capacitors. Now, energy stored in the first capacitor would be given by half C1 V1 square, right? Energy stored in the second capacitor would be given by half C2 V2 square. Similarly, energy stored in the third capacitor is given by half C3 V3 square. Also, it may be written as, there are 3 expressions for the energy stored in a capacitor. Also, it can be written as Q square by twice C1. It can be written as Q square by twice C2. And it can be written as Q square by twice C3. Or it may be written as half QV. It is half Q V2 and it is half Q So these are the three expressions for the energy stored in a capacitor. Or this has been done just previously, right? So total energy stored in the system. This is the system comprising of these three capacitors connected in series. So what our intention is to determine the expression for the total energy of this particular system, right? So what to do is, suppose it is replaced by this circuit. CS is the resultant capacitance of the series grouping of three capacitors, right? Charge, as you are aware, will remain constant, right? Q is constant. So obviously, and in terms of C, we can make use of this particular expression, Q square by twice C. So the energy stored, total energy stored in the system, it will be given by, this formula is to be used because your charge is constant. Q square divided by twice CS. CS is the resultant capacitance of the series grouping of the three capacitors under conservation. So what we can do is Q square by 2. We are aware in the series grouping, this CS, it's given by 1 by C1 plus 1 by C2 plus 1 by C3. This is the formula for the resultant capacitance in the series grouping. So 1 by CS over here can be replaced by 1 by C1 plus 1 by C2 plus 1 by C3. So this is the result which we will get, plus Q square divided by twice C3. So total energy would be equal to Q square by twice C1, it is U1. Q square by twice C2, it is U2. Q square by twice C3, it is U3. So it is U1 plus U2 plus U3. So what's the conclusion basically? When any number of capacitors are connected in series, then the resultant energy of the series grouping of capacitors is given by the sum of the energies stored in the individual capacitors. So that's the conclusion, right? So this is the case of series grouping. So remember, in the series grouping, out of these three expressions, this formula is to be used. Why? Because charge is constant in the series grouping. And we need to express our answer in terms of C, because the resultant capacitance of the series and parallel combination, its formula is known to us. Isn't it? So we can easily conclude this particular statement. Total energy of this system is given by sum of the energy stored in the individual capacitors. So students, let's proceed with the next one, in the parallel grouping, right? In the parallel grouping. Parallel grouping, you are aware, the capacitors are connected across one another in such a manner that the potential difference across the plates of each of the capacitor is same as that of the applied voltage. So let's consider the case of three capacitors connected in parallel. So let's consider this case. These are the three capacitors connected in parallel, and they must be connected across the same 2 points, so that the PD, potential difference across each of the capacitor, is same as that of the applied voltage. Right? These are the common points, A and B. This is suppose C1, this is C2, this is C3. Potential difference would be constant, because the plates of each of the three capacitors are connected between the same points A and B. So PD, potential difference across the plates of each of the capacitors, is same as that of the applied voltage. Now its equivalent diagram may be given by this. This is suppose C parallel. C parallel is the resultant capacitance of the parallel grouping of C1, C2 and C3, right? PD would be same. These are the 2 points AB, so B would be same. So total energy of the system, would be given by, here V is constant. So this formula is to be used, half CV square. So it will be given by half C parallel and V is constant. Clear? So proceeding further, we can write half V square. Now we are aware if the capacitors are connected in parallel, then the resultant capacitance in the parallel grouping is given by this particular formula, C1 plus C2 plus C3. This is the formula for finding the resultant capacitance of the parallel grouping of capacitors. So substituting this value of C parallel over here, we get C1 plus C2 plus C3. So what we get is half C1V square plus half C2V square plus half C3V square. So here V is constant and C1, C2, C3 are the capacitances. So total energy of the system, half C1V square, that's the individual energy stored in the first capacitor. It can be written as U1. Half C2V square, that's the energy stored in the capacitor 2. That may be represented as U2. And half C3V square is the energy stored in the third capacitor, which may be written as U3. So we get this particular result. So students, as you can observe, whether the capacitors are connected in series or they are connected in parallel, it is immaterial whether the capacitors are connected in series or parallel. In both the cases, the net energy of the system is given by the sum of the energies stored in the individual capacitors, right? So that's the verification of the above fact, right? So energy, total energy, I am talking about the total energy of this system, whether the system comprises of 3, 4 or any number of capacitors. Total energy of the system is always given by the algebraic sum of the energies stored in the individual capacitors. So students, I hope the topics which are being taught in this particular session must be clear to you all. Do practice and just be thorough with your understanding of the concepts, right? So all the best. We'll continue in the next session.